Hi, welcome to week 2 of this course, in which we're going to talk about quantitative methodology. So in this week's lecture, we're going to touch upon at least 4 of the major parts about quantitative methodology. We'll start by looking at what do we mean by statistical reasoning, and we look at variables, what they look like, and we're going to talk about measures and measurement, and lastly, we're going to talk about samples. So with me again, Dr. Yanto Chandra, today on the 17th of January 2023. Please respect the use of these materials in which any unauthorized use is strongly discouraged. Thank you. So if you remember from last week, we talked about different ways that we can approach truth through different philosophical perspectives and different types of processes, variants or process approach to get into closer to truth, and different kind of research traditions such as inductive versus deductive, and different issues in research such as unit of analysis, equifinality, parsimony, tautology. And then we talk about theory. We talk a lot about theory, and we also talk about the research process. And the key part of the research process is understanding how you come up with a good research question, and you do the rest of the part in order so that your research will make a good contribution to maybe theory, maybe to practice, maybe to help your company to do better, or to policy, maybe if you are public policy makers. So today's lecture is about, this is the part 1 of the 4-part of today's lecture. So this part 1 is about statistical reasoning. So what is statistical reasoning? When I think about it, wherever we are every day, we are dealing with some sort of statistics. So what is this thing called statistical reasoning or statistical thinking? A major part of it is some form of probability, right? When you turn on your TV in the morning, the weather forecaster is talking about what is the weather for today, right? With a certain chance of rain, with a certain temperature, right? When they say there's a certain chance of a rain for today and this week, that is not a very precise measurement of the weather. It's just a probability. It's not something very sure. It's not something that the weather forecaster is 100% sure. So they give some number, 30% chance, 40%, 50%, 100%. Whenever I rarely see 100% chance. I have only seen a 90-something% chance of rain. So it is a probability. So it's the possibility for an outcome to happen, right? When I was a student, a PhD student, I often went to, it's a place where people do betting on horses and on horses, or what we call the greyhound, right? So I was very attracted to this, not because I like gambling. I don't gamble. I don't think it's a good thing. But you can learn about statistics. When you go to this type of gambling places, the horses or the dogs doing the racing, right? How do you know which dog will win, right? So which number will win? So this is very much a very probability. There's so many variables that will determine whether that particular dog will win, right? Maybe how long his legs, his body is, and how strong his muscle is. But also maybe there are other factors like what happens to this dog the day before, the week before. Was he well? Did he eat well? Did he sleep well? Did he rest well? How is the relationship with the owner or the trainer? And what about the track, the length of the track, and the location of the track? So a different track, will affect the result of these dogs. Or if you are a woman or a couple who's trying to have a baby, and you wanted to know on what particular day it's good to have a sexual intercourse with your partner, and there's a particular chance or probability of getting pregnant. So you can talk to your doctor. The doctor can give you this, but the doctor will not give you 100% assurance that if you do a sexual intercourse on a particular time, on a particular date, it will be 100% guaranteed you will be pregnant. And then the same thing when the doctor talked to you about your chances of being a woman, what are your chances of getting pregnant at what particular age? This is also a matter of probability. For example, people who are much older, the probability of getting pregnant will be a lot lower because perhaps the ovum, the cells, the egg cells are likely to be lesser in quantity and maybe even quality compared to a younger woman who has a much higher chance of producing a lot more eggs and with a higher quality. So these all things is about probability. So statistical reasoning is really very much part of our life. Now let me ask you, how many of you go to the gym, push or pull the heavy things, right? So a good way to understand about the second part of statistical reasoning, which is about the distribution of a particular events or data, right? If you like to go to gym, please record every time that you go to gym, like how many kilograms can you lift? But if you take every gym goers, like let's say wherever gym that you go to, you ask them how much do you normally pull? How much is the weight that you can pull? And you capture everyone's in that gyms, right? And then you already have the stack of these iron bars, right? From 10 kilos to 150 kilos, right? If you check how many people can lift 10 kilos, how many people can lift 15 kilos, 30 kilos, 50 kilos, 70 kilos, 90 kilos, right? Maybe it happens that you are a very strong guy, you can lift 95 kilos, the one circle on the red there. But most of the people maybe can only lift around 45 kilograms, right? So every people that you asked, you can give a number, how many people can lift 10 kilos, how many people can lift 20 kilos, 50 kilos. So for each of this level, if you can get their number, and then you say how many people can lift a particular gram, if you draw that, it will look like a bell curve. And then bell curve, in order to read it, you need to look at, to turn your head. So it's actually, it will look like a bell curve. So this bell curve, which is about what we call normal distribution, a normal distribution will look like this. So where does this come from? Some very clever statisticians have done lots of studies and experiments to see what is the normal distributions of all kind of events. So they've gone through all kind of data, and they tend to find this normal distribution is a very, very common type of phenomena from how tall people. So when you look at people's height in the entire Hong Kong, the entire China, the entire United States, the entire world, you can get there's certain number of people who are here. And if you're extremely tall, you're most likely to be over here. Or if you're extremely short, you're more likely to be here, right? Or people's IQ, same. There's kind of a round average of people's IQ around this middle part. So this is where the average is, or the mean value is. And if you are IQ 200, you might be one of the very few. If you have IQ 250, you might be on one of the very few. So you are near the tail. Or if your IQ is very low, like 10 or 20, you might be also on this end of the tail. So, or you are buying pizza. In pizza, you record like how many minutes that your pizza arrives in your home after you make the order using your apps, right? And every time the pizza delivery guy comes, you record how many times. So if you plot that, you'll find an average time. For example, in this diagram, it shows that the average time is 30 minutes with a standard deviation of 5. Just here it says like it could be 5 minutes more than 30 and 5 minutes less than 30, right? So this is what we call normal distribution. Again, the normal distributions is very much an assumption used by what people call frequentist statistics. Eventually, the course that you learn today in this course is based on frequentist statistics. I have a friend who's a professor of mathematics and statistics in the UK, and he is actually a Bayesian statistics, and he made a lot of criticism on frequentist statistics, but he does teach frequentist statistics. But Bayesian is very different. They don't believe in a normal distribution because there is prior. You can talk about that. You can take some courses on Bayesian statistics. Another type of statistical reasoning is called correlation. Correlation is one of the most commonly talked about. And I'm sure you already know this. For example, you know that if you study harder, the more hours that you study, your exam results going to get better. So you will have a straight line. If you put the dots there, like let's say Mr. A study 8 hours and the exam result is here. Mr. B studied for 20 hours, which is here, and the exam result is here. So you take the line, so it's dot there. So you can put everyone's dot there, and you can draw a line to represent all of these data points. Data points is, you know, people's behavior or organization's outcome, and you can plot it there. You can see. So this is the correlations between X, which is how many hours you study, and your results of your exam. And so this is one type. Now, another type is, for example, how many people take flu vaccination, right? The result will be different because logically, the more people take flu vaccination, the number of people who get the flu will be smaller. So it will look like this, right? So there's one is positive like this, and one is negative like this, going down, right? But you can also see other kind of correlation. For example, you see, the number of the sales of organic food. People like organic food, right? People think organic food is healthy. But you also see an increasing number of people who are born or who grew up with autism. Is a psychological condition, right? And see, why are they running together? And also you look at the numbers in the newspapers that there's increasing number of shark attacks. Like we don't have shark attack in Hong Kong because people don't go a lot to the beach. But if you go in Australia or in other places, a lot of people spend their time in the beach, and a lot of shark attacking people who are swimming in the ocean. And you might also find that, well, there's also a similar pattern of ice cream sales. So the blue and the red line is very similar, or the blue and the purple line is very similar. Is this really correlation, or is it just by chance, or what people call spurious correlation? So we need to understand the different type of correlations and what do they really mean. So this is what we're going to talk about. Another important type of statistical reasoning is causation. Now, causation is about if you do X, you will cause a change in Y, right? For example, you are very sick, right? You go to see a doctor. The doctor asks you to take a medicine. You take the medicine. A few hours after that, you feel better, or you feel totally cured a few days later. So you can see there's a cause and effect, right? Because of you take medicine, the medicine will have some processes in the middle, and then you are cured at the end. So this is called, the two relations is called causation. This is different from the previous one called correlation. Correlation means they are just related. But in causation, this makes this happen. So without this, then this will not happen. I like to use a very interesting example here. Andy Lau. We all know Andy Lau, right? Andy Lau is one of the most, perhaps one of the most famous singers in Asia, right? From Hong Kong. So he has, you might ask, why does he look like that when he's already 60 plus years old, right? He's relatively slim with a very little body fat and almost six-pack. For the man, you like six-pack. And despite his age, he doesn't look that old. If you look at his photo when he was 20 years old with his being 60-year-old, I mean, the difference is not a stark difference, right? So in one of the newspaper, I pick up an interview with Andy Lau and the journalist, and he said he has been living with this 16-8 diet. So what is Andy Lau's 16-8 diet? So in Andy Lau's lifestyle, this is what he said in an interview: he will have empty stomach for 16 hours. So he will not eat anything for 16 hours, and only in 6 hours of the day he will eat. So he will eat within, so overall 24 hours, right? So in my theory, so this is my interpretation. I have a theory about Andy Lau's 16-8 diet. So my theory is a certain condition where you have empty stomach, right, was going to produce something good for your body. Maybe maybe your cells will regenerate, your blood will get better, cleans up, and it will lead to some positive health outcomes. So this is my theory, but this is based on Andy Lau's interview. So you can always form some sort of thing and to test whether there's actually a causation. For example, if Andy Lau practices for many years and it works for him, and you go and try this, right? So you have 6 hours empty stomach and you only ate in 8 hours per day, and you look at your health, or maybe your physique, how your physique look like, and the how much fat that you have in the body and things like that, and you measure that every 3 months, every 6 months, or 9 months, 1 year, and every year. And then if you really find that practicing 16-8 diet will really give you that type of physique or physical conditions, then you can say, wow, there's a causation between this 16-8 diet with a particular physical features, right? So this is another example. Another type of statistical reasoning is what we call prediction. So actually, this is what statistics is very powerful. You can use statistics to predict something. So when you say predict something, do you need some data to predict? The answer is yes, right? So for people who are learning statistics for the first time, they think statistics is like magic. It's like out of nothing, out of something, you can predict about the future. But that's not how it works, because statistics is part of science. In science, we need past events or past data in order to predict the future data. For example, I like this example. The relationship between happiness, right, with income, right? People say if you have lots of money, you'll feel very happy in your life, right? But is it really true for everyone? So if you're interested in one person, you can do a qualitative study and ask a person, are you happy? What is your income? That's it. So you get to know only the conclusion for one person. But if you are a statistician or learning to be a statistician, your interest is not on one person. If you're interested in one person or 5% or small groups of people, you should be a qualitative researcher. But if you're interested in a larger number of people, the entire city, the entire country, the entire world, then using statistics will allow you to get to know the relationships among those situations or conditions or variables. For example, if you want to know whether happiness is related to people's income, and this is just one example of some study that people have done. So you conduct a large-scale survey, you get tens of thousands or hundreds of thousands of people to fill in your survey, and each black dot there is each person. You ask them, how much is your salary? So there are some people who earn their over $14,000 or $15,000, very high there, and they're also very happy. And there are people down the bottom there who earn maybe less than 2,000 euros, and they're very unhappy. And there are a lot of people somewhere there. And then what statistics will do is, if you analyze these dots of data in your SPSS or R, it will produce a line of best fit, which is the red line, which give you a summary of the relationship between income and the happiness. Right? Income on the X and happiness on the Y-axis. So why we use statistics? Because it allows you to predict relationships among two variables. You can also use statistics to predict more than two variables on an outcome, right? For example, if you want to predict happiness, you can use income, but there may be other variables that predict happiness, right? Right. There are other factors that predict happiness, and you can include that in your study, for example, in your survey or in your experiments, to test if there are other factors apart from income that will predict happiness. And then we talk about something linear, something non-linear. So the previous example that I've seen is something linear, right? For example, you study more, or you study harder, you're going to get better results. So that is always a linear. So which means that if one goes up, the other variable also goes up. So when the independent variable goes up, the dependent variable also goes up. So when they both together goes up, this is called positive. When this goes down and the outcome is also going down, right? So this is called negative relationships. So which means that the change of 1 unit of X, when this is equal, to the change of 1 unit in Y, this is called linear relationships, right? But a lot of, not all, there are many relationships in this world that is not linear, or what we call them non-linear, or even curvilinear. So the one example there is that I show you is the level of conflict and the level of organizational performance. So I think, let's say you ask or you conduct a survey among 1,000 companies about, and you ask them, do you have conflicts in your organizations or not? So some organization will say, we have super high conflict and our organizational performance is here. And some will say, we have super low conflict and our organizational performance is here. And there are some who are, the conflict is over here and the performance is here. And some who are here and the performance is here. And then you plot, you run the SPSS, you run R to do the analysis, and it will give you this kind of line that looks like letter M, right? Small n. And this is what you find in the relationship between the level of conflict among the people in the organization and the organizational performance. Then this is actually curvilinear. So what this is actually telling us is that when you have too little conflict, maybe what too little conflict could mean, for example, it could mean that everyone just agree with each other and no one else is producing or proposing some ideas that is different from everyone else, right? So when there's little conflict, then the performance is not so good. But when everyone is keep on fighting because of they have different ideas, for example, or different ways of doing things in the organization, then you have too much fight, too much conflict that will reduce overall performance. But there is a certain point between these two that varies. That, for example, if your conflict is relatively medium, you may have a better performance than when you have totally no conflict or totally high conflict. So what is found here in this type of curvilinear, there's optimum point in the middle that would tells you if the conflict is around this level, then the organizational performance is going to be at this level. So what you're interested in to see, where is that point, and in why is this happening like this? This is what you can study, and this could be one possible outcomes of your research. And understanding this kind of relationship helps you a lot in providing advice to the chief executive officer, CEO of the organization, or if you are working for the government, you can give advice to the policymakers how to, for example, how much notice do you need to give to your citizens so that they pay tax online? They pay tax on time, because some people forget to pay tax. Some people do not pay tax. Some people pay tax too early or too late. So at what point, how should you remind the citizens so that they pay their tax on time, right? You can do different experiments, or you can do some survey to capture this to know what is the optimum. Maybe if you remind them too many times, they get annoyed and they even do not pay, or they will just ignore the deadline and pay later. Or when you don't have any announcement at all, people may forget. But maybe at a certain point, you remind them at a particular time, I don't know, 1 time, 2 times, 3 times in a year, then they will really pay tax on time. So this is just another example. Another type of thinking is outlier. What is outlier? Outlier is something that deviates from the majority, right? For example, if you go to New Zealand, or if you go to France, and they have a huge mass of land, a lot of ships, like hundreds of millions, or even hundreds of thousands or tens of thousands of ships, and some of them, most of them are a particular color, and one of them is actually a totally different color, like a brown color. So that brown color ship is actually an outlier. So what outlier is, it shows a behavior or some outcome that is different from the majority. So for example, you take a relationship between X. Yeah, you look at students. Yeah, you're studying students, why some students perform really well in school, right? And you say, oh, maybe this is attributable to how many hours they spend studying every week or every month or every semester, and what is the grade that they get on the y-axis, right? So how much spent efforts, time studying, and the grades that they get on the y-axis, right? And you get every individual. So some people only study 60 hours and they got around 60 something grade, and some people spend a lot of, let's say, 120 hours and they got a very high score of, let's say, 100, 120. We can rescale this to 100, but this is just an example, right? And then some people who study overly long hours, more than 140 hours, they get they only get the middle part of the score, not like the highest score. And people who are spending only 60 plus hours, they get like almost the top of the score in the scale, right? So you might ask, who is this number 1 and who is this number 3? And there are some people who are spending like 100 hours of studying and they get a very low grade, right? So this person number 1, number 2, and number 3 are actually outliers, right? Now the question is, in statistics, what do you do with these people? So there are some techniques that you can do. We'll do that later in the computer lab in the following weeks. Like if you have some outliers, what do you need to do? And this is not an example of you take the measurement of people's body and you find some of the people have like what 300 degrees Fahrenheit, and you say, well, this must be a superly different, right? Or you capture people's height. Most people is 170, 171, and you have someone who is 3 meters. So that 3 meters must be something very different. So you want to pay attention to that. So in most cases, people want to remove the outlier in their statistical analysis because these are making the results very, very noisy or very messy, if you like. Another type of statistical reasoning is what we call error. What is error? It's common sense, right? Error is there is something that is really true, right? And there is something that you think is true, right? So the thing that you think is true is what you measure. We call it measured value. And there's something that is really true. This is called the true value, right? Let's say I'm 170 centimeters tall, right? And then you are trying to measure me. When you measure me as you find that I'm 171. And some of you come and measure me and you found that I'm 169. And another person measure me and say I'm 169.5. So you have 3 values here, 171, 169, and 169.5. But what is my true height? My true value? My true height is 170. Right. So in statistics, the difference between my real value, my true value is 170, with that 171 that one of you have measured, and 169 and 169.5 that some of you have measured about me, about my height, that is called the error, right? So how many of you have gone to the bar that you play the darts, that you throw the dart at the wheels, right? So some of you, when you throw the dart, your dart will go everywhere. It stick, but it goes everywhere. So it's not accurate and it's not precise. So this is what we call, you have large random error. So the error is because you have a poor technique in throwing the dart. Now, let's say then you say, I'm going to use a kind of a gun to shoot this to the dart instead of using hand, right? And then when you shoot, you are very precise there. You don't move at all. Every time you shoot, it always go to a particular position, right? So this is not accurate, but it's precise. It's precisely going to a particular location, but it's not particularly accurate. This is what we call, you have small random error. The error is small, but the systematic error is quite high. And this systematic error is because of your instrument, right? For example, if you ask the wrong question in a survey, or you use the wrong activity for people to do in an experiment, right? You may have a systematic error. And this error is not because of the problem with the respondents or the participants. It's because of your instruments, or because the way that you design your research. And because of instruments or the way that you design your research is not very accurate. So it produces error in a systematic way. So the error is systematic, right? So which one is better? You have large random error or you have small random error? Of course, you want to have a small random error. If you have a systematic error, then your next job is to correct what is the problem with my measurement, with my survey instruments, or with my experimental treatment that I need to change so I can get accurate and precise. So accurate and precise is what you want. So accurate and precise is where your true value and your measured value is the same, or at least very close to each other. So our purpose as a researcher is we want our research result to be as accurate and as precise as possible. If you don't do that, you might end up with like the train, which the engineers didn't do a good job in calculating maybe the speed or the length of the track for the train, so that the train really crash through the windows and come out. So later when we talk about regression, I think it will be in week 4 and week 5, and then you have a regression coefficient that you can construct from the statistical analysis. So if you run SPSS or R to run regression, you're going to get some numbers, some results, which you can put together in an equation. And a part of the equation is actually error. Error is something that not fully captured, or it shows that there's something else going on that your main model, let's say your main variable is B, let's say here B0, your main variable is B1, B2, B3. These are each of the variable that you are, or your independent variable that you are measuring. And you can say that despite everything that you have measured with B1 and B2 and B3 for each of the independent variable that you are measuring, it will not 100% predict the Y, or the Y hat, the Y with the hat, right? Because there are some error. We're going to have a look at that later. Another type of statistics is error. So when we say error, is like different types of error. For example, if the alarm is ringing, right, and then the fire alarm is ringing, and and it rings so loud, and every one of us have to go down to the ground floor and wait until the the firefighters came to check, right? So if the firefighters come and check and actually there is no fire, that is one type of false, right? One type of error, right? One type of error. So people call it false alarm, right? So false alarm means that we thought there is a fire, that's why it rings, right? But eventually there is no fire. So you can call this as one type 1 error, right? Type 1 error, in which you think something is real, you think something is happening, or let's say a variable is significant, when in fact it is not significant, right? So and you typically call this type 1 error as alpha. Actually, when you do your analysis in SPSS, SPSS will spit out this alpha number for you. You don't have to worry. And another type of error is when you think, let's say there is actually a fire. There's a fire in the building, and then the fire alarm didn't work, and you sit there. All of us are still in the building, and suddenly someone just screamed, "Guys, there's a fire! Let's get out of the building!" And we all rushed out the building. And you say, "What happened to the fire alarm? Didn't it work?" Apparently, that fire alarm has a type 2 error. So the fire alarm didn't detect there is a fire. So the fire alarm doesn't reject the null hypothesis. The fire alarm didn't think that there is a fire. So that's why it doesn't ring. And we think it's fine, right? So there are type 2 or type 1 error. So this can always happen to any research. Another example is, to very easy understand about type 1, type 2 error is a man come to see a doctor, right? And we know that man will not be pregnant, right? At least, I don't know, for the next 50 or 100 years in which men do not naturally can get pregnant, unless in the future we can make men to be pregnant. But right now, men cannot be pregnant. And a doctor told this man, "Hey, you are pregnant." Then you know that this doctor is making type 1 error. So the null hypothesis is always there's no relationship between variables, right? Let's say the man is not pregnant. That is the null hypothesis. But he's saying you are pregnant. So he's saying the alternative hypothesis is true or is positive, where in fact it is not, right? So this is called type 1 error. The other type 2 error is a woman who is definitely pregnant and has been confirmed to be pregnant using X-rays and checking with the other doctor. And then he went to see another doctor, and that lady doctor said, "You're not pregnant. You're just having a big tummy." So this is called type 2 error. So she is already pregnant, right? But the doctor think this is not pregnant, right? So the evidence is there, the truth is already there, but the doctor is not able to say that this is the reality. So the doctor think this is not the reality. It's not the truth. So this is called type 2 error. So there are many ways to do with that. For example, so you have a reality. Look at the table on the most corner. There's a reality and what you test in your survey or in your experiment, right? If you're using these methods, right? So if your test results and the reality is the same, matches, then you have a correct, you can reject the H null and accept the H, you can have a correct rejection of H null. So that will give you power or 1 minus beta value. We're going to talk about it later. But so what you want is your test of reality, yeah, and the reality matches. So I think the one that matches is the one at the down bottom there. So correct acceptance, sorry, the horizontal is what we want, right? So what you test and what you get is both correct, right? So for example, you correctly reject the null hypothesis. Null hypothesis, I would say there's no relationship. So you correctly reject it, and which means that you say you accept that the null hypothesis, the alternative hypothesis is correct, right? Let me repeat. If your test is correct, and with the right reality, the reality is false, right? Then you correctly reject that there is no relationship, right? Or you correctly accept that there is no relationship, right? So that is how you see the type 1 and type 2 error. We're going to have a look at that later. Another part is statistical power, which is related to what I've just mentioned earlier on. So power is actually what is the probability of correctly rejecting the null hypothesis, okay? So when you say, wow, your experiment or your survey has no power. No power means it cannot detect whether the result is true or not true in a very strong, in a very confident way. So how do you know that the result of your survey or experiment will be very strong, in which you can correctly reject that there is no relationship? In which, or in other words, how can you show that your statistical results can support the hypothesis that you are proposing? That depends on the sample size. So that's why in quantitative study, you want to have a relatively larger sample size. So there is a limit sample size. When you do a survey, right? When you do a survey, let's say you have 20 variables, you don't want to survey only 5 people there, because your sample size will not give you enough power to reject that there's no relationship between studying hard with getting good results. If you want to verify the relationship between studying hard and getting good results, you need hundreds or even thousands of samples of people so that you can verify the relationship between these two. So when you say studying hard and getting good grades has no relationship, that's called null hypothesis. And your purpose as a researcher, you want to reject this. You want to show that studying hard will lead to better results, or taking this medicine result in better health, or you are cured from a particular disease. So that depends on the sample size. So you can calculate a sample size using a certain technique. There's a software to do that called G-Power. And there's a certain minimum level for statistical power, usually 0.8. But in most cases, people want a bigger than 0.8. Another commonly used statistical reason is called p-value. People always talk about p-value, but what is p-value really? It's about statistical significance. So if I draw a line here, if you pass this line, something is significant. If you below the line, something is not statistically significant. So for example, you say that if people study hard, they're going to get a better results in the exam, right? And then this conclusion is supported by the survey that you have done to 5,000 students, right? And your p-value is lesser than 0.05, or at least 0.05 lower, right? So 0. That is equal or lesser than 0.05 for the p-value, right? If you get this result, then basically this is good. So another way to interpret this p-value is to say that, so 5 or 0.05. The other part is 95%. So if you show that your result has this p-value of 0.05, it means that you can be confident that 95% of the people or 95% of the situation that the relationship is in a certain situation, and you are very certain that your error is very low, is only 5% or lower. So you can only look at p-value as a kind of like error, or the kind of getting your results by chance. You don't want to get your results by chance, because when it's by chance, there's a lot of error there, right? A lot of error, a lot of mistakes, right? You don't have a lot of mistakes. So with a lower p-value, your logic is saying that how true is your result? It has a high truth, 90% level of truth, because only 5% is most likely to be wrong. So in the same way, now if you have 0.01, right, or 1%, 0.001, sorry, 0.1%, 0.001, then you can say that 99.9 something percent, your result is more likely to be true, and your error is likely to be only around 0.01. So you want your p-value to be lower, right? So is there any differences? Yes. In social sciences, typically we are very happy if our results has a p-value of lesser than 0.05. But if you are in medical science, for example, you are formulating new drugs, new medicines for people, then you want to make sure that your medicine is very safe, right? That when people eat it, they will really be cured, or there's no harm to their body. So in medical science, they typically use a much smaller p-value, because they want to reduce the possibility of that mistakes or error. So there has to be lower p-value. But in social science, if you get 0.05 or lower, you are already very happy. And you can look at this value from the SPSS or R output after you run it in the analysis. So for example, if you want to know what factors predicts the mathematics achievement test of students in primary school, right? And so that is math achievement is your dependent variable, right? Remember we talked independent and dependent. And then you also ask in the questionnaire the father's education of the children, the mother's education, and their grades in high school, and their gender, right? And then you run analysis, and this is what SPSS give you, that then you can tell which one is significant, right? So which one do you look at? Because there's so many outputs there. You look at the column called significant, that one, right? So actually you can say that one is 0.544. So father's education is 0.54 is 50% something. So it means that it's not significant. It's more than 0.05, a lot more. Mother's education, 0.2 is also a lot more than 0.05 or 0.001. Remember, our threshold value is 0.05 or 0.01. So father's education and mother's education has nothing to do with the children's math achievement test. But look at their own grades in high school and their gender. It shows that there are grades. I think this may not be a math test achievements for children, because it's talking about the participants or the respondents' grades in high school. So let's say this is your math achievement test as a university student or as a master's student, right? So your grades in your previous years of education, right, is significantly contributing to your ability to get high grades in mathematics achievement test or not. So it's very significant, 0.00, which is lower than 0.01. So this is very significant. Gender is also very significant, 0.006. So it means that maybe either male or female do really well in the math achievements. And you can probe deeper to look at the mean difference between the male and female in terms of their mathematics achievement test. So this is just something to help you with. I'm near the end for the stats reasoning. The other type of stats reasoning is effect size. When you say effect size, it means like, for example, you take a medicine. Does it have effect? It really means that whether the intervention or whether a manipulation change some outcome variables that you want to see, right? For example, you have you have a group of students, right? Let's say this class, we have 130 students. I split you guys into 2 groups. The first 65 groups, I call you the green one. The first 65 groups, I teach you normally. Right? I deliver the lecture, I talk to you normally, right? So and then everyone get a result in your test, and then there's a grade. There's a grade in which the majority of the mean value of each one of your grade in this class is the one with the green line, the vertical green line. So the green bell curve is the grade for the first group, and your average score in your I don't know, GPA or whatever in this course is the one in the middle. And the second group, this another 65 group of students, I give you a lot of coaching. I bring you the best minds in statistics to coach you like every week, right? Amazing. So I'm gonna give you a lot more efforts in terms of giving you the best possible ways to get you learn more. And then I measure everyone's grades and same test, right? It has to be the same test between the green one and the purple one. And I got your results and I plot them. So I expect that the second group, because I bring in so much resources and efforts to help you, I expect your mean value, your mean score for everyone in the second groups in your exam or your overall results should be better than the first group. So there's a difference. The difference is called D. That's the difference. So effect size is actually that D. We want to see whether there is a difference between the 2 or more groups that you're comparing. So why is effect size important? Because it helps you build a cumulative understanding about a certain practice, a certain strategy, a certain intervention, and how it affects a certain outcome. For example, if I teach with a certain technique and students get these kind of results, and then other professors is using the same technique and they also get a similar results, then this becomes cumulative. That's the best practice is being built. And for example, if I say my company is using this strategy so that we can have a better financial performance, and there are also hundreds of thousands of other companies that are doing the same based on a survey or experiment, right? Then this evidence is cumulative, so we can be more and more confident that applying a certain strategy in the company will get you a better financial performance, right? So the purpose of this effect size is to know the relationship between a certain action or certain intervention with its outcome, right? And you want to see whether this applies to other research or other organizations or individuals, so that this helps us build the knowledge together. So effect size, they always call it a coherence D. That D is so there's a certain way to calculate it. We're going to look at it later when we look at the statistical results. So some effect is very large, considered large. Let's say more than 0.8 is considered large, or when you are lesser than 0.2 is considered very small. And if you're between 0.5 to 0.8, the result is considered moderate. So another important part of statistical reasoning is to know what kind of research questions that is suitable to be answered using quantitative methodology. Typically in quantitative methodology, you're trying to answer these type of questions. The question of what? People ask, what factors that make you do well as an employee? What factors that help companies earn a lot of money? What factors that help people to live longer, right? Extent is also another very commonly used. Like, to what extent does poverty influence the health of the poor people? To what extent is giving good education will help? It's very much with how much, right? So extent and how much is somehow very different. Like it tells about the extent. So the extent can only be answered using quantitative. When I say what can only be answered using quantitative, because you talk about a particular variable and you want to know whether that particular variable is significant or not. The same with which. Let's say you have a lot of variables. Let's say you have 10 variables, and you say which variable among these 10 variables is the most significant. Let's say you want to reduce poverty. Which one is the best intervention or approach to reduce poverty? Do you give them free cash transfer every month? Do you give them a lot of employment program? Do you give them free public housing? Or what else? So if you have a lot of options and you want to know which one is the best or which one is the highest, and we get to know this from a certain output from the statistics. For example, we can look at it from the beta coefficient from a regression analysis. So that will tell you the relative importance of one variable over other variables. So I stop it there. The next one is just talking about you have primary data, which are data that you collect yourself, or the data that others have collected and have been published. So so that's the end of statistical reasoning. I hope that's useful for everyone. And if you have any questions, you can always revise and review back the video. And thank you very much. In the next part, we're going to look at variables. Bye.